Welcome to the Agentic RAN, a joint demo between Northeastern University, Keysight Technologies, SoftBank, and zTouch networks. We'll show you how to create and use a large telco model to build truly autonomous radio access networks. We have three goals. First, automate intent-driven AI RAN. Second, optimize AI models with a large telco model, or LTM. And third, benchmark AI RAN performance in realistic wireless channels. Let's start with the problem. Network operators face constantly changing conditions. Capacity demands shift, interference patterns evolve, and not all of these changes are predictable. The question is, how can operators dynamically tune their networks using simple, high-level intents rather than manually configuring hundreds of parameters? Our answer is Agent RAN, a framework for truly autonomous networks built on agentic intent-to-network translation. Here's how the architecture works. The network operator provides a high-level intent. For example, prioritize emergency traffic, which is first processed by the Agent RAN manager, an AI agent in the non-real-time RAN Intelligent Controller, or RIC. This AI agent uses an LTM to process the input and provide sub-intents to layer-specific manager agents. These managers further break intents down into specific tasks for near real-time agents, which interact with DApps in the RAN and are eventually responsible for different radio resource management tasks. In this demo, we focus on MAC, or Layer 2, controls for power and scheduling. The whole system is supported by an AI RAN factory that handles AI ops and agent management. Now, how do we build these agents? We use two key capabilities. The Northeastern Open 6G AI RAN Lab provides the infrastructure for automating data collection and validation on an end-to-end programmable network. The RAN uses an open-source 5G stack with OpenAir interface and NVIDIA Aerial. The entire platform runs on the zTouch OS, which handles orchestration and automation. Keysight PropSim and RaySim provide a reel-to-SIM loop for high-fidelity wireless channel emulation. This means we can model realistic and controllable propagation conditions, including time-varying interference, and inject them into our testbed. The combination of Northeastern's AI RAN Lab and Keysight emulation solutions allows automated and continuous data collection, creating a feed for the LTM training. The workflow at the bottom shows the pipeline. We define a scenario, deploy the network stack, generate channel emulation conditions, collect data, and then generate trained agents. A key innovation in this work is SoftBank's Large Telecom Model, or LTM. The idea is to take a pre-trained base language model and perform continual pre-training and specific fine-tuning on telecom-specific data, public data, and composite proprietary data in a training-ready format. The training pipeline produces a large telecom model that can reason about network state and generate appropriate actions. Once agents are trained, we deploy them using zTouch Network's zTouch OS, which orchestrates the AI RAN deployment. It deploys RAN and core network, the Agent RAN agents, and handles AI RAN orchestration. The infrastructure itself follows the AI RAN paradigm, where compute resources at cell sites can be dynamically allocated between RAN processing and AI workloads. And here's the system running live. First, we run the Agent RAN with a pre-trained commercial LLM. We observe that it successfully translates our intent, save energy on the MTC device, with a minimum of 10 megabits per second into network configurations. However, some scenarios require knowledge of the exact deployment, not fully captured by the intent. Further, delays in using commercial APIs limit the effectiveness in real-time situations. For example, in a shared spectrum scenario, an operator asks the network to limit interference to neighboring cells, for example by blocking some PRBs. This needs to be dynamic. As soon as the probability of interference is reduced, the blocking should be deactivated. Using a generic LLM, one can see that the intent is often not successfully translated, or PRB blocking is applied and never removed. The control is imprecise, leading to interference reports. The SoftBank LTM, through its telco-specific knowledge, knows how to manage this situation and successfully mitigates interference, while dynamically unblocking resources. We can observe that the LTM successfully translates the operator intent by mitigating interference dynamically and autonomously. To wrap up, Agentic RAN brings together open source 5G infrastructure, high fidelity channel emulation, the large telco model, and agentic orchestration to deliver truly intent driven autonomous radio access networks. Thank you.